Here we present Bridging the Imitation Gap by Adaptive Insubordination. This is a collaboration between researchers at the Allen Institute for AI, the University of Illinois Urbana-Champaign, and the University of Washington. In this work, we study a phenomena we frequently observe in practice. Experts that are too smart can fail to teach their students optimal policies, even when optimizing perfectly. Consider a simple setting in the MiniGrid environment. The red triangle denotes the agent and its orientation, that is, looking down. The agent must navigate to the green goal. A well meaning expert sees the state and says, obviously, move forward. But this starting state of the agent is one of many. For instance, the agent could be facing left. Here, the expert says, obviously, turn left. Similarly, the expert might say that turning right or left are both correct, or that turning right is the only correct strategy. But now consider what our student observes in each of these settings. Rather than observing the full world state, the student agents frequently only have access to partial egocentric observations. In each of these states, the expert tells the student to follow different actions, even though from the student's perspective, all the states look exactly the same. More formally, we say that the observation seen by the agent is filtered by a function f. In this example, this filtration function maps four distinct environment states to the same partial observation O. Proposition 1 in our paper shows that in these cases, the student's policy is an average of the teacher's. Formally, let pi il be the policy among all possible student policies that minimizes the cross-entropy loss between itself and the expert. We show that pi il then equals its conditional expectation. To get some intuition, let's go through this equation step by step. We have that the student policy minimizing the cross-entropy loss evaluated at a partial observation equals the average of the expert policy evaluated over all world states which correspond to the same partial observation. In our original example, this means the student would never learn to consistently move in any direction. Thus, in many realistic settings, even if you were able to optimize perfectly, it is possible that a student will fail to imitate the expert. So, what are some solutions for this? We can design experts who operate on exactly the same observations as our student. For such experts, there is no imitation gap, but they can be hard to impossible to code, or when collecting human demonstrations, expensive to collect. We instead propose the adaptive insubordination methodology. Here, we used what we have learned about the imitation gap to adaptively weigh imitation learning and reinforcement learning losses at the train time. As a result of this weighing scheme, we show that we can solve tasks where other IL and RL methods fundamentally fail. For more information, please come talk with us at our poster and check out our paper. Thank you.